mainly on diagnostics and evaluation. And what we've done here is both that I've been working on diagnostics on coupled processes and evaluation of the extreme weather. I put together this presentation both together with people from the coupled processes team in the research department and the EFAS team working on flooding. So if we first start with a picture of system modeling, and we have seen quite a few of these days. But it's just to highlight what we currently do and currently not are doing in at DCWF. And to start with, where our history lies in the atmosphere and the forecast for the atmosphere. And that's still our main purpose, and we bring in other components primarily to serve the atmospheric forecast, but as I'm going to show later, they have a good use for themselves. So then the other components we have are the ocean and the ocean waves on top in the interface between the atmosphere and the sea. And then we have recently introduced the sea ice model in our coupled system. We have a land surface model, which includes the soil and also the snow on top of soil. And then we have lakes also included in the online calculation for the land surface. Then I forgot to put the text, but I put the factory here, showing that we're also doing some work on atmospheric composition within the Copernicus services. And then finally, we have rivers that I'm going to discuss more later. But then put to a process on what we're not currently doing. And first of all, we are not doing urban modeling. We, for example, do not have an urban or city tile in our model, and we are not handling irrigations. And also put the crossover the coast, which is a bit of a pity of the field we are down here for, but we do not have a storm surge model, and we are not doing any coupling between the rivers and the sea. So from this model system, we then can get out quite a lot of different type of forecast. And here put out some maps that some of them are from Hurricane Irma recently. So, for example, we have the wind and the wave fields coming out, precipitation, soil moisture. We are producing with forecast of river flow, but also flash flood forecasts. And snow, although it was quite hard now to find anywhere in the northern hemisphere where it has snow cover. And all this is done in an ensemble framework. So if I put up a table of the different model components we have and how they look in our high-resolution forecast, which is currently having a resolution in the atmosphere and in the soil components of 9 kilometers, run out to 10 days twice a day. And then the ensemble forecast that runs 15 days twice a day, but also twice a week we run our subseasonal system, which is just an extension of the ensemble system up to 46 days. And the ensemble system has a resolution of 18 kilometers for the 50 ensemble members now. And after day 15, in our subseasonal extension is 36 kilometers. So when we look at these atmospheric resolutions, and especially for the high-res, we start coming down to a scale that not so long ago was considered a limited area resolutions. And we're running into similar type of modeling problems that was evident 10, 50 years ago in the limited area community. But it also gives possibilities to do some more refined products, so to say, look into processes that we weren't able to capture before. Then for the other couple of components, we have for the soil, we run the H-Tessel model. And then for the lakes, we use the flake. And for waves, ocean waves, the European Center version of the one model, running on the 14 and 28 kilometer resolution. And then for ocean and sea ice, we use the NEMO model and the LIM model for the ice. And the resolution we use is the 1/4 degree. And currently it's only our ensemble system that's coupled. But in our next model upgrade that will come hopefully around Christmas, we will actually put in the ocean coupling also to our high-res forecast. So after that, all our forecast system will be coupled to the ocean. And then for the rivers, we are the computational center for the Oceânico service that runs EFAS, and the model component is the LIS flood, which runs with a river routing network of 5 kilometers for the high-res and for the ensemble. But it runs in an offline mode, so we calculate the river discharge after our coupled simulation is finished. So it's 3 key messages I want to highlight here. What you are doing are medium range forecasts. That is our main focus. And then we're running a global model. And then we have a strong focus on the ensemble. But the focus on the medium range and global put the constraints on the resolutions and also how detailed we can be in some processes that have been discussed here earlier this week.
I'm sorry. Yeah. Perhaps I missed it, but will you be increasing the resolution of the NEMO for the high-res?
No, we are going to stick with a 1/4 degree.
Okay.
So some words about the Copernicus service of the global European and global flood awareness system. I use that acronym EFAS and GLOFAS. So the EFAS is the European component, which I said using the LIS flood, and it provides products to European hydromet services and civil protections, where the GLOFAS is run for all parts but not Europe, and it's publicly available for registered users. And it produces both medium range forecast and seasonal forecast for the EFAS, and up to a sub-seasonal scale for the GLOFAS. So it's much longer time scale that we have been discussing for some products here, but clearly the resolution is a limitation for a system like the GLOFAS. And there's also a difference where the EFAS uses the soil model from a LIS flood. The GLOFAS use the output direct from H-Tessel, which have mainly been developed for the atmospheric coupling. But it's a step towards a more integrated use of the soil models. So in order to illustrate the different type of products and capabilities we have, I worked out from our archive three different examples that I'm going to use. Is Hurricane Sandy that we already have discussed here a couple of times. It's a case of coastal rainfall over northwestern Italy a little bit less than a year ago, and then a windstorm over the North Sea a couple of years ago. We try, when we see some interesting cases of extreme weather that we think will be good for evaluation later on, or test the model, we put it into a database and save some of the plots and put in some evaluation plots. So we can go back, and it's also publicly available if you want to see how we have performed for different type of extreme cases. You can take a look. So if we start with the Hurricane Sandy, and it's an example of the storm surge and the waves mainly, as have been discussed, and also parts of the precipitation. And I think it's also caused some problems with snow, if I remember right, up in the Appalachian Mountains. And if you look at the ensemble forecast from roughly 5 days before, when the cyclone was south of the Dominican Republic, we see this plume of the tracks with a huge spread. And I like this example because it's like the school book of what we sometimes discuss with an ensemble and having a clear bifurcation. And this is probably the most illustrative bifurcation I've seen, but it also illustrates the spread and the uncertainty that what was in the forecast on this time range, both in whether or not make landfall, where to make landfall, and all these dots are the different positions at the time when the landfall actually occurred. So it was also a timing issue. And we made a study a couple of years ago and looking into different aspects of the forecasts. And one aspect we looked into was the forecast of significant wave height, and looked into different resolutions of our forecast system. Starting with around 60 kilometer, around 30 kilometer, around 16 kilometer, and then we run an experimental run with 5 kilometer resolution. And each plot here shows the significant wave height with New York City here, Long Island. And then we had two good buoy measurements that we could look into how well they performed. And in black here you see the observations, and each line here are the different resolutions, starting with the lowest resolution in green, then going to blue, then red and orange. And the top one is the mean sea level pressure, and the two highest resolution was quite good here because they had a good timing of the system. This helps us to compare with the observations. And if you look into both the wind speed and the wave height, especially for the wave height with the highest resolution, we see for the buoy furthest to the west and closest to the coast that we really started to capture the peak of the wave height. So we're not there yet with 5 kilometer resolution, but in our fairly ambitious strategy, we have said that before 2025 we should be down to 5 kilometer resolution. Then another aspect to look into is the total precipitation for the same set of forecasts. And here's the next road product showing the forecast. And especially we see with the orographic features that are visible, well captured in the higher resolution, but not in the lower resolution. So that's another, and we return to that in a minute, important aspect for the coast, how well the model is to handle the orographic precipitation. So that we come back to in example 2 here, which was a rainfall event from November 2016 that was fairly major up in the northwestern corner of Italy. This was one station here that they got more than 400 millimeters in 24 hours. So the top plot here shows the observations where each black dot is more than 300 millimeters. And then we look at a 1 to 2 day forecast from our high resolution system, and it peaks around 150 millimeters, and that's not bad. We consider it quite good for being a global system, but it's still a factor 2 off, or even more if we consider the highest one. So it's where the resolution and probably also the handling of the cloud processes in the models are important to how fast the rainfall is created over orographic features. And then just to show you how our surface model was handling this event for different variables. So how it looked inside each test, and I took out a point here, and where the blue is the hourly rainfall, and the black is the runoff created for this grid point. And we see that in the beginning, it's not so much of the rainfall that goes into runoff, but instead we see that it goes into the water storage. But in the middle of the plot, all the layers in the surface model are saturated, and everything goes to surface runoff or the precipitation. It would have been flagged as a flash flood that we're soon going to see. But this is a short-range forecast, and as I said, our main concern are the medium range. Of course, to create a good short-range forecast, a medium-range forecast, we need to have a good short-range forecast. So, but looking into longer scales, for the same example, this is a product we created that we call the Extreme Forecast Index, and it's for precipitation. And the index is calculated by comparing the PDF, or rather the cumulative version, the CDF of the ensemble forecast, and compare it to the CDF from the model climatology created for our current version of the model. So the further yellow and red, the further away are the distribution in the ensemble compared to the climatology for that point, for that time of the year. There's no surprise when we look into 1 to 2 day forecast that up in this corner is saturated around the value of 1. However, if you look into 6 to 7 day forecast, the colors are more pale, but this area was already a week before highlighted as a potential area for extreme rainfall. And if you look into an analysis on the day of the extreme event, in order to try to explain this predictability, we see cut-off flow in Western Mediterranean, and a strong southerly flow hitting the orography. And this was also well captured in our deterministic forecast roughly a week before. That it was that large-scale forcing that was the key to capture this event. And if you look into diagnostics of atmospheric rivers for this event, we indeed see that it was a strong atmospheric river hitting the orography on the coast on that day. We took out this plot only a week ago, so we haven't had time yet to explain how the atmospheric river managed to cross the Sahara. So, and then, as I said, we also produced offline the flood forecasting products, and this is our short-range flash flood product. That's actually not this using the output from the SMWF forecast, but from a Italian version of the Cosmo model that downscales the SMWF ensemble. But anyway, we see that it put out a lot of warnings along the Italian coast for flash floods, and the return periods went up to 50, 100 years. It was indeed flagged as an extreme event. And then also for larger rivers, this is River Taru, and I suppose it's up here. We also see that this rainfall caused flooding in larger river systems. So then the third type of example of coastal flooding, and we bring up, is more related to ocean waves and wind speed and pressure. Typically during the autumn wind in the North Sea, where we, for this case, had a cyclone rapidly developed and brought strong winds with the wind gusts up to 50 meters per second in Denmark, and high waves. And also here, if we look into the same type of product, the extreme forecast index, but for maximum wind gusts, we see the event when it happened, or the day before it happened on the 5th of December, we have saturated colors more or less of the whole North Sea and the areas around. But if we go back roughly a week, we already here see that it was flagged as a potentially extreme day. And as I said, we are not doing any storm surge modeling at ECMWF, but some of our member states, of course, using our model output to do the storm surge model. So this is from the Netherlands for the case I just described, just to illustrate the product and the severeness of the sea height and the storm surge they predicted. So to start to summarize what I said so far, so starting with what we are doing is medium range forecast and also longer range. I mentioned the sub-seasonal, but also the seasonal system. Then a global Earth system model with atmosphere, ocean, waves, soil. But because it's a global system, it puts limitation of what resolution we can put in. We put in all the components into an ensemble system, and then we have the river discharge products via the EFA service. Then what's more interesting is what we currently not are doing. Some of them currently not, or some that we will not do. First of all, limited area models, although one can see the EFA's European domain as a limited area, but generally speaking, all the components we put in with a global domain. And not the storm surge modeling. And then we're not doing any urban modeling, which could for local flash floods be interesting to have in, but also for the events like heat islands during heat waves. We're not doing any inundation maps. So finally, what are our challenges? It's not only the challenges from the CWF side, but I think for all of us. First question, is the skill in the medium range is sufficient to be useful? So even if we can illustrate that one see a signal a week out, is that the information enough to take any for anyone to take any actions? And I put here just one verification plot which shows potential economical value, which is a measure of the potential value over a range of uses defined by a cost-loss ratio for the actions. And if you look into day 7 forecast, this is for precipitation, but looks similar for wind speed. We see they're only non-zero, but only positive potential value is for very low ratios, which means that the cost of the action is very low compared to the potential loss. But that is maybe not bad, because the action a week before is more heads up action. So start being aware or be prepared. Be aware that in a couple of days you needs to start to prepare for an action. But while for shorter forecast is day 3 and day 1, we're spending more uses. Then another challenge for the predictability point of view is timing errors. And if thinking of storm surges and how they interact with the tides, with the example of Hurricane Sandy, we saw it was in the shorter forecast when the plume started to narrow. There was still a timing difference of plus minus 6 hours, and that's more or less each side of the tidal cycle, which could be used, or which would amplify the uncertainty range in the storm surge model. Then it's always that the devil is in the details. That even if I see the risk in a large area, to really pinpoint, as we saw in the example yesterday about the flash floods in Italy, to really pinpoint exact where is the question if we're going to be able to do and how to communicate the uncertainties. And finally, as we had in the previous talk, that keep the all-time clock limit for the model. We of course want to put in more and more components and with higher and higher resolution, but we need to be able to deliver the forecast in time every day. So with that, I'll stop and see questions.
So the first question is your EFAS system. You have evaluated the quality. We understand it is uncoupled, so it's run after. And you have evaluated the quality across Europe. Is there a difference between, regional difference between the skill in your forecast? Is there some reference, for example, literature?
Good question. We just did it for longer time scales for the seasonal. So for that, we have a new results for the medium range. I suppose we have that, I need to ask. But for the seasonal scale is use differences in time of the year where one can gain predictability from snow melt and the initialization of snowpack. Get higher predictability, especially over the Iberian Peninsula. We have problems with how to handle underground water flows, and then of course the human impact and the regulations on the river flows is causing a scientific problem.
So I was wondering, was your couple system coupled with the wind? So in the ensemble system, do you also do the ocean ensemble, ocean wave ensemble?
Yes.
And so is there a data simulation also in those lake and ocean?
Yes. So the wave is included in the atmospheric initial conditions. I'm not up to date with the details how the initial conditions when we run a data simulation. But for the ocean, we run the 3D VAR system with I think we can run it with 5 ensemble members in the data simulation.
And then the next question is, how often do you do the coupling?
Good question. I think it's about every hour. So, when it's, I mean, that's my best guess. That's 1 hour. It used to be 6 hours, but when we increased the resolution, we increased the frequency of the coupling.
For the low fast, I guess fast, but I'm mostly interested in low fast. Do you compute also the extreme frequency index for VII or whatever it's called?
Not exactly, but we calculate the model climatology. Okay, so we get it.
So you provide a probability with respect, an exceedance probability with respect to that?
Yes, okay. The return periods. Because coupled to our ensemble system, we also have a reforecast data set that spans the past 20 years, which we can use to calculate the climatological PDF.
And for the climatology and for flow fast, the initial conditions are computed in a similar way?
That's currently the drawback. Yeah. So with the modern climatology, we're striving to have a system that is as close as possible to our real-time system, but we cannot afford to rerun a reanalysis for every new model cycle, so we have to start it on the year interim. We're looking forward when we soon upgrade it to the ERA 5 reanalysis, but especially for the land surface conditions, yes, it's a large difference between the real-time system and basically we run with the ERIM reinforcing, but they are offline experiments with the recent version of the land model. But that's so that makes them more similar, but the real-time land systems still have the data simulation component that we're not getting in the offline. So we still see in some parts of the world a mismatch between the reforecast and the real-time forecast.
Do you have documentation on that? Because I'm interested in that specific issue. Do you know what's documented? It's in fact using like a different way to initialize.
I can look back when we forward where I put some technical note on it.
Okay, I'd be very interested.
Can we get the data downloaded automatically, or it's just visual? Or you just visualize
it depends which part of the system you're thinking of. the atmospheric forecast for the GLOFAS or for the GLOFAS,
Yeah.
believe.
Except in you.
So outside Europe, you don't have enough thing. It says through web interface and FTP. So my guess is that on the FTP it should be binary data, but you can contact us and we can see.
I've done it, so I know you can do it. I know I did it through the WMS server, but I'm sure there's a better way. I didn't know that there was an FTP.
So did you do it? I mean, did you say that you were succeeded?
Yes, I succeeded, but I think through your mapping, so I don't think it was so if there's an FTP server that's better. So I had like a workaround.
Did you do it recently?
Other question?
Did you simulate Sunday with EC1 in offline mode in order to see the impact of the wake coupling?
I didn't do it. I don't know whether Sean did it, but these runs are in couple.
It's to wake up.
Yeah.
Yeah. I'm asking if you have any kind of results in offline mode uncoupled.
No, not that I'm aware of, but if you contact some below, you might have.
So if I may have another question now, about the ensemble now. So, I mean, for flood forecasting. So if you do use your typical ECMWF ensemble, you get very large perturbations because the atmosphere is really different. But that's not the real uncertainty in the surface field. Surface field is much less uncertain to a certain degree because there is topography, there is a lot of control by the boundary. So do you feel that there is a problem there in your using your EPS or ensemble system, which is done for different reasons, to do ensemble forecast in river?
Hopefully, this damping of the uncertainty should be done explicitly inside the model. And that it's a good question. We've been discussing whether to look into it more systematically, whether the hydrologic putting in an ensemble with the large spread into the hydrological model, whether the hydrological model is damping the spread or amplifying. If it's damping it, if it's damped it with the right magnitude. It's an interesting question.
Anything else? All right, thank you. We'll hear from Alfonso next.